All right, so here we are, video number 2 on rational functions. And in this video, we're going to talk about asymptotes, which is something that probably you've never heard of before. It's kind of a unique concept in advanced algebra and some classes that come after Algebra 2. But this is probably the first time you've heard that word. Uh, um, so this whole video is all about talking about, first of all, what is it? And then second of all, with regard to rational functions, how do you find them? All right, so really that's our learning objectives, and that's what we're going to go over in this particular video. So what is an asymptote? And again, remember, for our class, we're just looking for working definitions. You won't have to know an exact word-for-word definition. In fact, to really understand the actual formal definition of an asymptote requires a little bit of familiarity with calculus. And so we're not there yet. So when we talk about asymptotes and we define them, we're just going to come up with sort of a working definition, something that gets the basic idea across. But if you were to go to some more advanced math classes, you might find that you would have to tweak our definition just a little bit to make it a little more formal, a little more stronger, a little more powerful to deal with certain situations that we're not going to worry about in our class. Okay? But then once we know what asymptotes are, we're going to find them. And in our class, we're only going to have two types, vertical asymptotes and horizontal asymptotes. In more advanced classes, you might learn about other things like slant asymptotes and such. So you might have friends who talk about this depending on what classes they're in. But in our class, we're only going to worry about two, horizontal and vertical. And of course, we know what horizontal and vertical are because we've talked about X and Y axes, right? Horizontal is going across the page, horizontally across. Vertical is going up and down on the page, vertically up and down. And so some asymptotes go up and down, they're vertical. Some asymptotes go horizontal, they go across. All right, so those are our learning objectives. Let's get started with an asymptote and talking about just what exactly it is. And to do that, I think the easiest thing is to look at a graph and look at a picture. And so what I'm going to do is share with you an image that I've got graphed on my computer here, so you can see this. And it's just the most basic or the most simple version of a rational function. It's the function 1 over x, okay? So in this function 1 over x, the graph here are the red curves. And so we talked a little bit about before that with rational functions, you end up with these two parts. So here I've got a part in the top right-hand side. So notice there, if you look at the numbers, this is my y-axis, right? And this is my x-axis. And so I've got one part of my graph over my function that's up here on the right-hand side, quadrant number 1. And I've got another part that's down here on the left-hand side in quadrant number 3. Okay, and the way this particular graphing program works is if I click on the function's graph, it puts a point wherever I click. And then I can drag that point along, and you can see the coordinates that go to that point. So like right there, if I can get it, it's pretty good. There's 0.11, okay? And down over here is the point, -1, -1. Okay, so by dragging these points around, you can see coordinates. Now, here's what I want you to notice with this asymptote. I'm going to move our graph over. So as you can see, the asymptote here, as we go to the left, it's coming up, 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 up towards the x-axis, or yeah, towards the x-axis. But take a look at the y coordinate on that point, okay? The y coordinate right here, I'm at x equals -9. The y coordinate is -0.111, okay? Which just happens to be the decimal equivalent of -1 over 9, 1/9. And that should make sense because look, if I plugged a 9 in for x, I'd get 1 over 9. So -0.1 repeating, that should make sense that that's what we're getting there, okay? But here's what I want you to notice. As I move out the axis here, my y number is getting smaller and smaller and smaller, but my graph also has basically gotten flat, right? So I can see the y number is getting a little bit smaller, so it's not quite flat. But my graph is so flat that the y numbers aren't, even though my x number changes a lot, right? There I'm at 19, here I'm at 15, but my y number, it barely changed at all. 0.0, what, 0.01, 0.012 maybe? Really small, okay? And so what happens if we were to progress this out and go way out as far as we could possibly go, and look at decimal expansions of these numbers, what we would find is that this graph comes up towards the x-axis, but it never actually crosses it. So I'm just going to zoom out a little bit and pull out. And so you can see I'm here at negative 100, negative 200, and my red graph is definitely not crossing the x-axis. And if I was able to look at enough decimal places, I would find that not only is it not crossing the x-axis, it's actually not even touching the x-axis. And so let's think about this for just a second. Here's negative 500. X equals negative 500 right here. If I were to put that number into this fraction, I'd have 1 over negative 500. Now, there's no doubt that that is going to make a decimal that's tiny, a tiny decimal, but it's still a decimal. It's not 0 yet. If you round it off, is it close to 0? Sure, it's close to 0. And that's why my graph looks like it's right up here by the x-axis. But does it equal 0? No. No, it doesn't. It's just a little teeny decimal. And if you think about it, it doesn't matter what number I plug in right here. When I divide 1 by something, I never get 0 as the answer. I might get teeny tiny decimals that round off to 0, but I never get exactly 0. And that's the idea of an asymptote. In this case, the x-axis would be my asymptote. Okay, so let's think about how is the x-axis acting in this situation? Well, first of all, it's a horizontal line. So this would be a horizontal asymptote. And it's a line that my function, now my function is not a line. My function very clearly curves and turns. But my function, as x gets really large in the negative direction, my function gets close to that line without touching it. And the same thing would happen in the positive direction. So if I look out here, there's positive 20. So my y number is a little tiny positive number. And I can keep going out and out. And again, just like it was in the negative direction, my graph comes right down next to the x-axis, but it doesn't ever cross it. So here I'm at positive 500, and my graph is still not crossing the axis. And again, if I plug 500 into this, I'm going to get a tiny decimal, but it's not going to be 0. So once again, not only is the graph not crossing it, it's not even touching it because it doesn't equal 0. It's really close, but it doesn't actually touch it. All right, and so that's the idea of an asymptote. All right, so let me switch over here for just a second, and let's write that down. On my paper here, whoops, sorry, that was the wrong button. Let's try this button. There we go. On my paper, I'm going to write down that basic idea, okay? The idea of an asymptote. And again, I guess you could call this a working definition or something. I hesitate to call it a definition because if you get it stuck in your head that this is exactly what an asymptote is, when you get into more advanced math classes, what I'm about to write down will cause you trouble. It'll cause you problems. But for our class, this is going to be good enough. It's an idea. And the idea is the asymptote, or an asymptote, is a line that the graph of a function approaches without touching. Okay, the asymptote is a line. So first of all, that's what it is, right? The asymptote itself is a line. In our class, all of our asymptotes are going to be lines. So when you are, anytime you're working with an asymptote, it's always going to be a line, all right? And specifically, it's a line that the graph of a function approaches without touching. Approaches without touching. So notice the function is not a line. The very fact that it's approaching a line without touching it means the function has to be curving. It has to be bending. It's almost like the asymptote is this force field that the function, it's shooting in towards, but as it gets closer to that force field, the force of the field turns the thing around and it pushes it down. And I can't quite cross that boundary. I can't quite cross that barrier. Okay, so that's the idea of an asymptote. It's a line that the graph of the function approaches without touching. All right, now let me switch back again for just a second. And let's look at that graph one more time. So in this graph here, I want you to notice that the x-axis is one of those sorts of lines. It's a line that the graph approaches without touching. Whoops, I didn't mean to do that. I'm struggling with these notes. Thanks for being patient with me. There we go. So the x-axis, oh, now our function's blue. Well, there you go. I'm not sure why it changed, but whatever. All right, so the x-axis is a line that our function approaches but doesn't actually ever touch, okay? So that's the first thing. But I want you to also notice that because of the way the function curves up, the y-axis is working the exact same way. As I scooch up along my y-axis, I see that same behavior. My graph is approaching the y-axis, but notice my x number there isn't quite 0. And we know that if you're actually on the y-axis, the x number is going to be 0. So I'm close to the y-axis, but I'm not quite touching it. And the same thing is going to happen. I can zoom way out, go all the way up. You know, we can go up to positive 500 again, whatever. And what we'll find, again, is the graph never crosses it. And in fact, it actually doesn't even touch it. It gets really close, but it doesn't quite touch, all right? So that's the idea of a vertical asymptote. The x-axis then would be a horizontal asymptote. I've zoomed out too far, it's hard to get back. There's our origin, okay. So I've got a horizontal asymptote in the x-axis, a horizontal line that the graph is approaching without touching, and I have a vertical asymptote in the y-axis, a vertical line that the graph approaches without touching. All right, so this is the idea of an asymptote. In our class, all of our asymptotes will either be vertical or horizontal, one or the other. We won't have any exceptions. And so you're going to always be looking for either a vertical line, that's going to be a vertical asymptote, or you're going to be looking for a horizontal line, that's a horizontal asymptote, that the graph approaches without touching. All right, so that's what they are. Now, how do you find them? It turns out that vertical asymptotes actually are not very hard to find. And this goes back into the idea of why we have a vertical asymptote in the first place. And we talked a little bit about this in yesterday's video. The idea is that vertical asymptotes will happen if you have an x value that causes you to divide by 0. So I'm just going to put VA for vertical asymptotes. I hope that's okay with you. But vertical asymptotes will happen they'll occur only at the spots where the denominator equals 0. Now again, as we write this denominator equals 0, I do want to just put a little caveat here that this is true in our class. All of our vertical asymptotes will happen anytime the denominator equals 0. Again, as you get into more advanced math classes, it is possible that the denominator could equal 0 and you don't get a vertical asymptote, but that won't happen in our class, okay? It's also possible to get a vertical asymptote even if the denominator is not equal 0, specifically when we're working with functions that are not rational, okay? So there are other kinds of functions that also have asymptotes, and we're gonna study some of those later in the school year. So just be ready for that. Just because horizontal asymptotes or rational functions have asymptotes because you divide by 0, that doesn't mean they're the only kind of functions that have asymptotes. And we're going to get into that later. But when it comes to vertical asymptotes that are associated with rational functions, when it comes to horizontal or vertical asymptotes associated with rational functions, we will find them only in the places where the denominator is equal to 0. All right, so let's do an example where we do that. Example number 1. Find the equation of the vertical asymptote of f of x equals 1 over 2x minus 5. Excuse me, 1 over 2x minus 5. Find the equation of the vertical asymptote of f of x equals 1 over 2x minus 5. Okay, so in this equation, we have said that the asymptotes will occur only when the denominator equals 0. So if I want to find that asymptote, I'm going to set the denominator equal to 0. Now that should sound familiar, right? When else do we set the denominator equal to 0? Well, just in yesterday's video, we did that anytime we were trying to find breaks in our domain. So it happens that the asymptotes are going to occur only at places where the domain is broken. All right, so in this case, I'm going to solve. So I'll add 5 to both sides. And I'll divide both sides by 2. And I get 5 halves. Now, yesterday, what we said was that number tells me the exceptions to my domain. So yesterday, we would have said that this means that the domain of function f is all the real numbers except for 5 halves. But now and that's still true. That hasn't changed. But now we're adding on to that concept. Not only is 5 halves a number that you cannot plug into the function, 5 halves is also the spot where the vertical asymptote will occur. So this tells me that x equals 5 halves is a vertical asymptote. Okay, now x equals 5 halves, why is that? Remember, vertical lines have equations, but the equations of vertical lines do not look like y equals mx plus b. The equations of vertical lines look like x equals a number. And so that's what we have. We have x equals a number. So this is the equation of a vertical line. And specifically, it's the vertical line at 5 over 2. Right? So to kind of help with this, what I'd like to do is take a look at one of these graphs again. So let's graph this particular function. So we're going to change this function. Instead of being y equals 1 over x, we're going to make it y equals 1 over 2x minus 5. Okay, so there's my function right there. Y equals 2f minus 5. Now, we said that we were going to get a vertical asymptote at x equals 5 over 2. Excuse me. So 5 over 2, that's 2.5. Right? 2.5, that's 5 over 2. So if you look at our graph right here, 2.5, here's 2, here's 3. So 2.5 is right about here. In fact, we can put that in. Let's put in the point 2.5 comma 0. Okay, so there's where 2.5 is, right there. There's 2.5. So we can see that this graph looks like it's coming in that direction. But when we get to this neighborhood, the graph starts shooting down on one side and it starts shooting up on the other side. Okay. In fact, you know what? Why graph just that point? Why not graph the whole asymptote? So let's do that real quick. Let's graph x equals 5 over 2. And there it is. X equals 5 over 2. So notice x equals 5 over 2. There's my vertical line of x equals 5 over 2, or 2.5, however you want to say it. And the function, just like we had before with the y-axis, the function is curling up, getting close to that line on this side, and it's curling down, getting close to that line on this side. And so there is our vertical asymptote. And this was the process that we used to find it. Set the denominator equal to 0, solve the denominator, and this is both an exception to your domain, but also this is one of your asymptotes. Okay, so that's how you find vertical asymptotes. Really, as long as you were comfortable with this from yesterday, vertical asymptotes are fairly straightforward. Horizontal asymptotes, on the other hand, are a little bit less, well, it's a longer process. It's a little less convenient. Now, if you get to use a note card or your notes on tests and quizzes, then what I'm about to show you really isn't much of a problem, because there's simply a test that you apply. And as long as you can remember the test, you're good to go. Of course, the issue is if you don't get to use a note card or notes, then you have to memorize this test, okay? Fortunately, in our class, we let you use your notes. So here's the way the test works. Okay, so finding horizontal asymptotes, we use a test, okay? Now, the test works basically in two parts. The first part is actually the test itself, and then the second part is reading the results to the test, okay? So here's the test. Compare the degree of the numerator of the rational function to the degree of the denominator. Compare the degree of the numerator to the degree of the denominator. And remember that word degree, what that word refers to is the largest exponent in our polynomial. So if we think back to yesterday, exponent of our polynomial, if we think back to yesterday, we said our rational function is going to be a ratio of two polynomials. So polynomial on top, polynomial on the bottom, ratio of two polynomials. And the degree then is going to be the largest exponent in those top polynomials. So the first thing we're going to do is we're going to compare them. So let's take a look at an example real quick. For example, let's say that I've got the function 2x plus 5 over x squared minus 4x plus 1. Okay? I want to compare the degrees. So my largest exponent down here, that's very clearly a 2. There's no doubt. That's the only exponent I can see. So that must be the biggest exponent. In the top, remember this x has a sneaky ninja 1. And remember that anytime there's not an x, that's like an x to the 0 power, okay? So the biggest exponent in the top is the 1. So the numerator, its degree is equal to 1. The denominator, its degree is equal to 2. And if I want to compare those, 1 is smaller than 2. 1 is less than 2. So that's what we mean by when we say compare the degrees. So this is my actual test results. 1 is less than 2. Now, what does that mean? How do we use that? So this is the second part. Once we've done that comparison, here's how you read the results. Interpreting the results. Okay, so three things could possibly happen. The first thing is exactly what happened right here. The degree of the top could be smaller than the degree of the bottom. 1 is less than 2. The degree of the top is smaller than the degree of the bottom. So that's the first thing that could happen. If the degree of the numerator is less than the degree of the denominator, then the equation of the horizontal asymptote will be, the horizontal asymptote will be y equals 0. Y equals 0. So remember, horizontal lines also have equations, and the equations of horizontal lines always look like y equals a number. Y equals a number. And that's exactly what I have here. Y equals a number. So that's the equation of a horizontal line. Specifically, in this case, that's the equation of the x-axis, right? The x-axis, that's the horizontal line where y equals 0. So this particular function right here has this for its horizontal asymptote, okay? We can look at that real fast and verify that, okay? Now, we did not find the vertical asymptotes of this particular function, so don't worry about what the vertical asymptotes look like right now, but let's verify that the horizontal asymptotes do appear to be well, that there's only one, and it appears to be the x-axis. Okay, so there's our graph. And it certainly appears as I go out this part of my graph that I'm approaching but not quite touching the x-axis. And the same thing happens here. So the x-axis is indeed a horizontal asymptote. Now this function is interesting because it's got this other stuff going on. And if you think about it, that should kind of make sense, because if I set the denominator equal to 0, it has a power of 2, which means I'm going to get 2 answers, which means this is going to have 2 vertical asymptotes. And I see that, right? There's a vertical asymptote shooting up here, and then it jumps down here. There's another vertical asymptote falling down here, and then it jumps up here. Okay, so that's, by the time we get to the end of the week, you will be able to make graphs like this. We're not there yet, but that's coming soon. Okay, so there we go. That is the idea of the first possibility of our test result, the situation where the numerator is smaller than the denominator. But of course, other things could possibly happen, right? They could be equal. If the degrees are equal, that could also happen. If the degrees are equal, this is probably for most people the trickiest case to deal with. If the degrees are equal, then what you do is you use the equation. I'm just going to put HA for horizontal asymptote to save a little bit of time here. The horizontal asymptote will be the equation y equals, and then we're going to have a fraction. And the fraction is going to be the leading coefficient from the numerator over the leading coefficient from the denominator. Okay, so remember the leading coefficient, that's the number that comes first in the equation, the number that's in front of your leading term. So up here, my leading coefficient here was a 2. My leading coefficient down here was a ninja 1. Okay. Now, this test result doesn't apply to this because my exponents weren't equal. So let's look at a situation real quick where that happens. So for example, if I have the function 3x squared minus 5 divided by a 7x squared plus x minus 12, if those are my two functions, when I compare my exponents, when I compare my degrees, they both have an exponent of 2. 2 equals 2. So for my horizontal asymptote, I take the equation y equals, and I make a fraction. In the top of the fraction, I put the leading coefficient from the top equation, from the top polynomial. So that's a 3. And in the bottom of my fraction, I put the leading coefficient from the other polynomial. So that's a 7. So y equals 3 over 7, that would be my horizontal asymptote. Okay. That is definitely the trickiest scenario to deal with. And once you do this a few times, you'll get used to that. Of course, it's nice that you'll have your notes and you can always refer to your notes. All right, now there's one final thing that could happen. Remember our test, backing all the way up here, our test was to compare the degrees. So one thing that could happen is the top could be smaller than the bottom. That's what we saw in the first situation. Another thing that could happen is the top could equal the bottom. That's what we saw in our second situation. So the third thing that could happen is that the top, the degree of the numerator could be greater than the degree of the denominator. That's the third thing that could happen. And if that happens, then there is no horizontal asymptote. Okay. Now this is where if you get into a more advanced class, you might talk about how to handle this situation. It turns out if the degrees are exactly 1 off, then there is an asymptote. It's just diagonal. So they call that a slant asymptote. And if the degrees are more than 1 off, if this was a 2 and if this was a 2 and this was like a 4, then your asymptote is going to be shaped like a parabola, not like a line. And weird things start to happen. So in our class, all we're going to ask you to do is just simply say that if this is smaller than that, that there's no horizontal asymptote. And that'll be good enough for our class. All right. So let's wrap up this video with a quick example of what that would look like. All right. So for example, if I have the function j of x is equal to x to the fourth plus 5x minus 7 over x squared plus 2x minus 4. Again, I'm going to find the degree of the top. In this case, that's a 4. And the largest exponent in the bottom, in this case, that's a 2. The top is bigger than the bottom. So that tells me I'm in case number 3. If the degree of the top is bigger than the degree of the bottom, then there's no horizontal asymptote. So this tells me no horizontal asymptote. Okay, so those are the 4 things that you're going to need to do all together for this particular homework assignment. 1, find vertical asymptotes by setting the denominator equal to 0 and solving. 2, find horizontal asymptotes in the situation where it happens to be the x-axis. You'll know that's true because the degree of the top will be smaller than the bottom. 3, find situations where the degree are equal. And so to find the horizontal asymptote, you have to make this fraction. And then the final thing is to recognize situations where there's not a horizontal asymptote. All right, so that takes care of everything for this video. We've explained what asymptotes are, and then we've talked about how to find both vertical and horizontal. Thanks for watching. Have a good one.